Hello and welcome to the Energy Storage at PNNL webinar series, which is well aligned with our upcoming grid storage launchpad facility. This facility is designed to develop, test, validate, and accelerate the deployment of new clean energy technologies. I'm your host, Ram Devanathan, Division Director of the Energy Processes and Materials Division at PNNL. This division is home to many innovators who are advancing the decarbonization of our economy. One such innovator is our speaker today, Dr. Jamie Holladay. Dr. Holladay joined PNNL in 2000 and has been working on solving our nation's energy problems ever since. He is the 2021 Distinguished Inventor of Battelle, and this honor goes to people who have obtained 14 or more US patents while employed by Battelle. For more than 2 decades at PNNL, Jamie has directed his research towards enabling new and existing energy resources that are low cost and environmentally friendly. His current research focuses on high temperature electrolysis for clean hydrogen production and conversion of waste carbon to renewable fuels and products. Jamie also finds time to be the group leader of the Energy and Environment Directorate, and he's also a subsector manager for the Hydrogen and Fuel Cell Technologies Office. He's clearly a very accomplished gentleman, and it's my pleasure to welcome Jamie to deliver the webinar today.
Good afternoon, good morning, and afternoon to those of you out there. I'm excited to be here today to talk to you about something I love, and that's hydrogen. And I hope you enjoy this presentation. So without further ado, I am going to share my screen and we'll get started. Can you all see it?
Jamie, we can see it. It looks great.
Thank you. So today I'm going to talk about the motivation, what's going on with the Hydrogen and Fuel Cell Office, tell you a little bit about the different components for when you start talking about hydrogen for energy storage, what the different components in the system go to, and then some of the efficiencies and review some cost analysis that are available and that have been done in this area. So I hope you enjoy this presentation. Recently, for the motivation, a recent analysis has been done on what happens when we start doing deep penetration of renewables and with removal of baseline carbon sources such as natural gas or coal. This is an example here that is in the process of being published by some of my coworkers. And this looked at the California ISO system, and they said if we ran that at 100% renewables and no nuclear or natural gas for baseline, just with the hydropower, you get these areas where you have nice generation surplus, which is pretty exciting. But you also get areas where you're going to have generation deficits, and spanning this is over the a typical year. And for details, you'll need to check out that article. But as you can see, that we do have substantial areas of deficits, and that translates not just into power, but also requires energy storage, a lot of energy storage for long periods of time. With the red arrow, you can see here weekly energy deficit in the order of millions of megawatt hours for substantial part of the year. And then you also have weekly surpluses. And so how can we start balancing these things out? This is really the motivation for looking at a lot of the energy storage that we do with hydrogen, because we're looking at it for we're looking at it for long-term energy storage and seasonal energy storage. And so the Hydrogen and Fuel Cell Office has this vision. It's called H2 at Scale. And it's where we want to use hydrogen to enable low carbon power grid and to decarbonize different areas of our society. And specifically, it's focused on areas that are hard to electrify. And so you have here with the hydrogen connected with the grid as a way to enable these different areas in the decarbonization. And now hydrogen, a lot of people ask me, you know, how does hydrogen compare or compete with batteries? Well, I view hydrogen as complementary to batteries. Batteries are really, really good in some areas, and that's where batteries can be used. We should use them. And then when you get to other areas where you need maybe it's a little bit more energy storage or longer term, hydrogen starts looking good, and it complements pumped hydro and compressed air and other energy storage options that are out there. So this is sort of one of the visions that we have, and where we do it is I don't see it as competition, I see it as complementary to many of the other processes that are out there. So there has been a considerable amount of interest in clean hydrogen throughout the U.S. You may have heard of it. So here's a couple examples. We in Centralia, Washington, they announced 300 megawatts where they're going to make for electrolyzers. Delta, Utah, they've converted a coal plant to a natural gas plant, and now they're converting that natural gas plant. They want to run it on hydrogen, and they want to use geologic storage for that. And so you can see the nuclear industry is about it. Stanford is involved. So there's a lot of different areas where people are considering this hydrogen for considering clean hydrogen. And you can, this results is that there are about 620 megawatts of electrolyzer capacity operational or under construction as reported by the Department of Energy. And of course, this does not include 300 megawatts that was recently announced for Centralia. So we're closer, we're approaching a gigawatt here of capacity, which is very exciting for us in the hydrogen and electrolyzer world. But why are people kind of interested in this? And here is a nice little example from Douglas PUD here in Washington State. Douglas PUD has quite a bit of resources. They have hydro, they have wind and solar, and they're with the wind and solar, they've had the challenges of the renewable intermittency. And so they're ramping their hydropower up and down to account for the variation going on. And that variation is not just daily or hourly, but there's a great deal of seasonal variation in the wind and solar that's available out there. And so that's created lots of challenges for them. And particularly, one of the big challenges they have is the hydropower is not designed to ramp up and down. And so ramping it up and down, the generator sets is really causing them a large increase in maintenance costs. And so here's an example that they've shown is what of some of their generation set points. You can see, you know, the hydro wants to run steady, but they're seeing periods of time where they have to ramp it down, they ramp it back up, and fairly quickly do that. And that's their primary concern. So they want to levelize this out by using an electrolyzer. So they've bought a 5 megawatt electrolyzer from Cummins that they're installing and going to be making that hydrogen. And the wear and tear, savings on the wear and tear will probably, they believe, will cover the cost of the electrolyzer, future costs of the electrolyzer. Plus, it gives them another thing to sell. And so they're actually going to be selling the hydrogen they generate with their plans on a planned filling station that should be built near where they're located. And so that filling station before long haul trucks. And so they're very excited about this way of helping, you know, increasing the productivity, decreasing their maintenance costs, and this new idea that they get another additional resource that they get to sell. And that's what hydrogen does. It gives you energy storage. I call it energy storage with benefits. And so your typical system, you have your electricity generation, it goes to an electrolyzer, you store it, then when you want to put it back onto the grid, you just have some sort of power to grid like a fuel cell, and it goes back to the grid. You can any sort of system you have in energy storage. With hydrogen now, you now have a little bit more complicated scene. You can see now we can take that hydrogen, we can put it back on the grid. That we can definitely do. Or we can sell it. We can use it for re-electrification. We can use it for buildings. We can use it to make fuels. We can use it as a fuel, or we can sell it for industrial products such as making ammonia. There's a lot of interest in that. And so this gives you more options that you can do, as well as you can store it for very long periods of time without having to worry about it degrading over time. So the hydrogen will be good for days, months, or years, depending on how you store it, of course. And so we'll talk about some of these different areas. I'm going to talk about some of the major components very quickly. That's the electrolyzer, how we store it, and then the power generation, the fuel cells. And so what is a fuel cell? Of course, a fuel cell takes hydrogen and oxygen from the air and it electrochemically reacts them to make water and electricity. And this can be fairly efficient. We're getting pretty good at this. The companies have been working on this for many, many years. We use it, it's been used in outer space, and there are actually cars deployed. And I'll talk a little bit more about where some of the current applications are, but very briefly. Now, the question is, where do we get the hydrogen? Most of our hydrogen today, about 97% or so, is made from steam methane reforming. And so you take methane and the natural gas, and primarily methane, and you break that into hydrogen and carbon dioxide. And that's a good way to do it. It's very efficient. It's low cost, but you do produce that CO2. So there's a lot of interest and research on making what we call clean hydrogen. And clean hydrogen is defined as hydrogen that when you produce it, you make less than 2 kilograms of carbon dioxide per kilogram of hydrogen produced. That's the official Department of Energy definition. And so we can use a process called electrolysis, which is very similar to running the fuel cell in reverse, where we have the water inside of our electrolyzer, we apply a voltage there, and we make hydrogen. It comes out one compartment and oxygen comes out the other. We usually just let the oxygen go, and then we store the hydrogen. And today, hydrogen is principally produced where you have refineries and ammonia production. So here's the sites in the US where hydrogen is made. If I overlaid this map with refineries and where ammonia facilities are, it'd be identical. That's where the vast majority of hydrogen is currently made. But there's a lot of efforts to change that in the near future. People ask me, why do I want a fuel cell? Well, the value proposition for a fuel cell is productivity. One of the big areas that they're looking at fuel cells is in forklifts. So there's 60 to 70,000 hydrogen powered forklifts out there. And the reason is that companies such as Costco, Amazon, Walmart are moving towards it, is it's increased productivity. They last longer and they can recharge faster, fill time in minutes. And then it's also modular. And so, during this is now a bit dated, but back during super hurricane Sandy in New Jersey, they had 5 sites that operated for over 100. When the grid was down there, the 5 areas that had power were all fuel cells. They're modular, they're able to run for over 100 hours, and those ones happen to run on natural gas, but we could do the same thing with hydrogen. So it's pretty exciting. With hydrogen, the value proposition is versatility. And I took this slide, I kind of enjoy this slide, the Swiss Army knife here, where you can see, I'm not going to go through all of these, but it's so useful. You can use it in aviation for making aviation fuels. We currently use it for making all of our petroleum products. It's used in shipping, freight, transport. We can generate power with it, and we can make chemicals with it. So there's so much you can do with it. It makes it very, very useful, and we can make it from a lot of different sources. And so the Department of Energy Fuel Cell and Technology Office is looking to accelerate all these hydrogen technologies with a primary focus on decarbonization. So they work from production to delivery to storage and end uses. And recently they announced what's called the hydrogen shot. And we're pretty excited about this. It was launched last year, and there's going to be in the infrastructure bill, which I'll talk about briefly for 1 minute, you'll see how much support the Department of Energy and the administration is doing for that. The goal of the hydrogen shot is to lower the cost of hydrogen production to $1 for 1 kilogram of hydrogen, and to do that cost reduction in about a decade. Now, just to let you know, people say, well, how much energy is 1 kilogram of hydrogen? Well, you can think of it as a kilogram of hydrogen has about the same energy as a gallon of gasoline. So that should help you understand about what those costs and what the energy looks like. And so recently, you've probably seen the bipartisan infrastructure bill. There's a lot out there for energy storage, but there's also a lot out there for hydrogen. There's 4 main different areas. They have the clean electrolysis program, which we're very excited about, looking to decrease the cost of electrolyzers. There's about $1 billion over 5 years. The clean hydrogen manufacturing and recycling is looking how to decrease the manufacturing of the hydrogen different components, whether that be a fuel cell, compressor, or storage, and also how to recycle, because a lot of times some of the electrolyzers and the fuel cells do use precious metal catalysts, and so we're going to want to capture those and bring them back to decrease the cost and to make things more efficient, and also design these systems for recycling. And so they have about $500 million over 5 years for this particular program. There's the regional clean hydrogen hubs, and this is really to build up the infrastructure for clean hydrogen. And this is the one that people are most excited about. It's a $8 billion, nominally over 5 years, though it'll probably be run longer, about 7 to 8 years. And where they want to build anywhere from at least 4 hubs is in the law. Most likely you'll be somewhere between 7 and 10 hubs that are going to be across the United States in diverse areas, that from using diverse fuels, and by fuels I mean like renewables or fossil with carbon capture, CCS, or nuclear or what have you. And this is a deployment effort where they're going to be building up both the production, storage, delivery, and use will be in each of these hubs. And these hubs, by being stationed throughout the United States, will start creating this network and advancing it and helping to lower the cost of hydrogen while making it a sustainable and clean source for us. And then, of course, they're working on a strategy and roadmap. So what you might have noticed is yesterday, the Department of Energy, in addition to the regular bill funding, they have the Hydrogen and Fuel Cell Office does get their own appropriations. And yesterday they announced their intent to issue a funding opportunity. And what I thought might be very interesting for this community is the area of interest 2, which is improving electricity grid resilience and a formation of a university research consortia to, as it says from the notice of intent, establish a regionally diverse university research consortia to support states and tribes individually, regionally, in developing tools, data analysis, plans, criteria, and methods to enable use of hydrogen for electricity grid resilience programs. And you can find more information about this on EERE Exchange. One thing that kind of surprised me was they call it a notice of intent 0002792, but they also have another reference to 2807, so which kind of confused me. So I just want to make sure you're aware of that. But if you go to the EER Exchange website, you can find out more. And we'll make these slides available, and this will be in that deck. So now, what are the different types of fuel cells and electrolyzer systems? And you have a low temperature, high temperature. We have what's called a proton exchange memory system. We have alkaline systems. We have solid oxide systems. There are a lot of them out there. So just rather than going through all of them in details, here's just a few highlights. Looking at the efficiency, the most efficient systems right now would be a solid oxide, and this is looking at the fuel cell, electrolyzer, then round trip. and you know, the solid oxide fuel cells about 65%. The electrolyzers can be very high, 70 to 85% or more, and with a round trip efficiency of very exciting of 40 to 50%. The PEM fuel cell and electrolyzers, the fuel cells are about the same efficiency, but the electrolyzers a little bit lower system efficiencies. They're working on increasing that, and round trip efficiencies around 30 to 35%. The alkaline really, they don't have there are some forms of alkaline fuel cells, but they're not really largely established. The electrolyzer, though, they tend to be a little bit lower efficiency. And so, but there are great numbers of these out there, though they are working and learning how to operate them differently to increase the efficiencies to above 50%. The challenges, you know, the operation temperature is always of interest. I put this on here. The PEM and alkaline are what we call low temperature systems, operating 60 to 80 degrees, and that's pretty easy to handle, whereas the solid oxide system operates at 700 to 800 degrees Celsius. And so that's the area that people cause concerns. Once you've heated it up, they just run and they'll be self-heating, but that does that may be, I just wanted to point that out. So it is because of the higher temperatures that they are able to get to these higher efficiencies, of course. And then everyone asks me, how much do they cost? Well, capital cost. Solid oxides tend to be low because they don't have a lot of precious materials in there, at least they have the potential to be low. There's currently a lot of research. This is the least developed of the technologies. And so we're focusing on that. In fact, I just came from a meeting with a consortia where we're dealing just with how to improve the performance and lower the cost of solid oxide electrolyzers. PNNL and all the national labs are heavily involved in that. PEMs tend to be a little bit more expensive. They tend to use a lot of precious metals such as platinum and iridium. And so their capital cost tends to be higher, with alkaline also being a lower cost because they avoid the use of precious metals. And alkaline are by far the most available technologies out there. They've been out there for a long time. For example, PEMs, we can buy megawatt scale systems. Alkalines, you can see here's the 5 megawatt scale systems. Alkaline, they have many years experience, and they can have multi-megawatt level systems that are available, whereas the solid oxide they're starting to deploy some of these systems. They're working up, they're in the 10 to a couple hundred kilowatt range, and then you put them together to make a modular system and build up. So that's sort of in a nutshell, a little bit about the different technologies out there for the electrolyzers. That's the hydrogen generation, and then the power generations. So we got, and then this is just how do they compare? How does hydrogen energy storage compare with other types of energy storage systems out there? And so you can see the lithium-ion batteries, lead-acid batteries, compressed air, pumped storage hydro tend to be a bit higher, particularly than the PEM and the fuel cell system, PEM electrolyzer system. The solid oxide system has the potential to get up there and be very competitive. What excites me, something unique about the solid oxide system that you don't have with the PEM system is the possibility of a reversible system. So we can make the solid oxide fuel cell and the electrolyte be the same unit. So it increases your capital utilization, and we should be able to do that. The early data that we're seeing is that the efficiencies will stay the same, and so if we can keep that by having, rather than having two separate systems as they're currently shown here. So when we're generating power, your electrolyzer is sitting idle. When you're generating hydrogen, your fuel cell sitting idle. You never want capital equipment sitting idle. If we have a reversible system, you have better utilization, which always helps your cost. And so that's something that we're very excited about, and it's a potential that we'd like to develop more. Now, how do we store the hydrogen? And there's a lot of different ways of doing that. I'm going to touch on what we call hydrogen carrier, liquid hydrogen, compressed hydrogen, and then briefly on geologic storage, which is very similar, you'll see, to natural gas storage. And so for hydrogen carriers, what we're looking at is some way of using a chemical to store the hydrogen on site and then release that through various means, perhaps heat or a catalytic reactor, on demand. And so an example that we're developing here, we're developing, there's a lot of different chemistries that we're looking at, but one we're developing uses essentially baking soda. It's a carbonate system where you add it, you store it as a powder, then you can add water to it, and so and it'll stay as a powder for as long as you want. You add water to it and you flow it through your system. You can release your hydrogen, and then you can regenerate the carbonate by using hydrogen from an electrolyzer. And so this is a reversible system. It's a very exciting system that we're very interested in. But there's a lot of different ones that are out there. And so here's some of the different systems. So we have what's called a reversible hydrogen carrier, a non-reversible hydrogen carrier. So these are ones we can decompose, and then you can't, it's harder to regenerate. And then I put on here the pure hydrogen, and here's the energy density per cubic meter, so you can get a feel for these different types of systems. So we have the reversible systems are exciting because, using ethanol to ethanoic acid, you don't completely break down the ethanol. You're just pulling some hydrogen off, and you can reattach it using an electrochemical reactor. Dibenzylthiophene is something that's very familiar out there, and ethyl 5 carboxamido adenosine is another one, and methylcyclohexane is a very common one. That's a six carbon ring where you pull the hydrogen off and on again. And the nice thing is that it's a reversible system. You do have to have hydrogen on there, and it's kind of fun. Looking at the non-reversible systems, this is when you get to things like methanol. A lot of people have talked about using ammonia as a hydrogen carrier, because we can store it, and you can store it, and it has a large energy density. Of course, there's some safety concerns with the ammonia and toxicity concerns, even with methanol. There's some there also, but you can see that we have, how do they compare to hydrogen? Well, hydrogen, of course, how much you store depends upon the pressure you have, or you can store it in liquid. And typical storage is around 350 to 500 bars compressed hydrogen, and the energy density you can see is relatively low, whereas the liquid gets pretty high. But there's challenges with each of these. And please remember that these systems, this is the energy density of the carriers. That doesn't include the reactor and things like that. So liquid hydrogen, as I said before, has a very nice energy density. It's 2.3 megawatt hours per cubic meter, and we really like it for logistics. It's good. You do have to keep it very cold. It's 20 Kelvin, which is about minus 400 and some degrees Fahrenheit. So it is cold, but NASA's learned how to handle this. We know how to hold it, and the challenge you have is if you don't use it for a long period of time, or even use part of it for a long period of time, you do get some losses there. So boil off is a challenge. But we do like it for logistics, things like that, and it's much more compact. And by logistics, what I mean is if you have a compressed hydrogen tanker, you're storing anywhere from 1,000, anywhere from the current, most of them right now is 300 kilograms per tanker. The next generation, newest generation, using composite tanks, there's about 1,100 kilograms of hydrogen per tanker. So that's okay. That's good. It's good to get up there. Liquid, we're over 4,000 kilograms of hydrogen. So if you're going to be moving this out to, say, a filling station, so a long haul truck filling station wants to use anywhere from 4 to 10,000 kilograms of hydrogen per day. That's an awful lot of tanker trucks if you're using compressed, but more reasonable if you're using liquid. And so moving it around, that's why we kind of like the liquid hydrogen, but it is good for different applications. Compressed gas, as I said, this is the most common. You can use the different types of tanks. You usually operate 250 or 500 bar. There are other higher storage tanks, but typically for most, if you're just going to use it for energy storage and not for filling up, these are the typical pressures that you'll be operating at. Most of the tanks are steel. That's the most common. They're looking at carbon fiber tanks more for onboard storage because they tend to be more expensive. And some of the innovation is that they're looking at cement tanks and lower cost tanks, which are very exciting. Then, of course, you can use pipelines. So if you have a hydrogen pipeline, you can pack it kind of like what we do with natural gas. And you can see, you know, the storage amount you're storing depends on how big their tank is. And then there's geologic storage, and there's active research and development looking at, okay, can we do it in, you know, the different types of formations that are out there. Salt caverns are the most preferred. They're the tightest, you lose the less, you don't get as much any contaminants coming in, but we can also, so that's the preferred one, and there's actually some demonstrations looking at that. Aquifers is next, and then depleted gas fields, and there's even talks of you know, engineering rock caverns and even abandoned mines for doing this. Of course, the advantages for geologic storage is they're very large, they're long-term. After you can make them, they can be low cost. Typical pressure ranges go from 70 to 280 bar. So I refer back to, you know, you're around these energy densities. The challenges, of course, is you have to cost of engineering it, locating it, making sure if you want to convert existing tanks, existing natural gas. There's a lot of talk converting existing natural gas pipelines and geologic storage, use material compatibility challenges, and then making sure your hydrogen stays pure, and then hydrogen loss, because there's different ways it can diffuse through, or you can have some reactions there. Hydrogen is a very small molecule, so it's a little bit harder. Well, it is harder to contain than natural gas. But this slide just shows you where these geologic formations are in the United States, and you can see that depending on the type, they're spread out throughout the United States, which is the good news. And so we're pretty excited about this. And if you have questions about it, I'd be happy to talk to you later about it offline. And then people ask me, well, getting back to, can you use natural gas infrastructure? And the answer is, yes, sort of. We're looking at it. There's some challenges out there, and that is hydrogen does have some different characteristics than natural gas, and it does cause what's called hydrogen embrittlement. And so there's an active project that PNNL is part of. It has about 20 different industrial partners and about 6 or 7 national labs studying this challenge, because it is a big challenge, because we would really like to start greening the natural gas by adding hydrogen, but at what level can we do it? And then eventually get to how can we repurpose these assets to using even up to pure hydrogen. And so the challenge is looking at how, you know, the different types of pipelines, the structural integrity. You know, your transmission pipelines are going to be steel, but then again, there's different grades, because some of these are very, very old, some are rarely new. The newest distribution pipelines can be plastic, polyethylene. And how does that work? How does it work in the residential end uses and things like that? And so we're looking at all these different things. We have an additional projects looking at the compatibility to reduce leakages, to reduce these challenges there, to ensure safety, and that all the hydrogen we make stays contained and we get to use it where we want to. Now, the last part that I'm going to talk about, spend a little bit more time on, is we are working with others at the Department of Energy to understand what the cost is for these technologies. There's 2 different things I'm going to talk about quickly. One is the cost analysis done by the Energy Storage Grand Challenge, and another is a tool that Dee Wu, one of my coworkers, has been working on developing, called the Hydrogen Energy Storage Techno-Economic Asset Model, or HSET. And so using as part of the hydrogen Energy Storage Grand Challenge, we call this is looking at hydrogen as what they call a bi-directional energy storage asset, means it charges and goes back and forth. And here are some of they made, if you go to this website, you can find all the different assumptions, such as 31% round trip efficiency, using cavern storage, using a PEM fuel cell and electrolyzer, since the PEM fuel cell has the highest efficiency of technologies that are available today. Solid oxide would be nice, but it's not quite as available right now. And the electrolyzer, they've projected the installed cost to be pretty pricey right now, $2,800 to $3,500 per kilowatt, a little bit more reasonable for kilowatt hour because of that large turn cavern storage. But with the funding that's being done and the really the push by the Department of Energy and the and industrial stakeholders to lower the cost of electrolyzers and fuel cells, they project that by as soon as 2030 we're going to see these costs cut in half. And we also project that the round trip efficiency will be going up. So, but you can find out more details about how they did this and all the ranges here at this website. Of course, this is the capital cost, and this was for the 100 megawatts and 10 hours of storage. What about how does this, compare both the capital cost and per kilowatt hour? And so again, that studies that have done here, you can see we've compared hydrogen with compressed air energy storage, pumped storage hydropower, lithium ion. They actually looked at several different types of lithium ion. I'm just showing the lithium iron phosphate, lead acid, and vanadium redox flow. And you can see that hydrogen, as the installed cost looks, for 100 megawatts is looking pretty competitive. And then as we go down, as we increase in the hours of operation, how many hours we want the 100 megawatt system to operate, you can see that the costs drop quite a bit. And that's where hydrogen is its advantage. It shows that for long duration, seasonal type storage, this makes it kind of interesting. At 1,000 megawatt, it's again looks like K's right now is one of the more interesting ones. But hydrogen is going to be cost competitive, especially when we get to the longer hour storage. And remember, one of the advantages or one of the things to consider when we're looking at hydrogen is that we're not just going to use it for bidirectional. I'll get to that in a second, but where we can get there. So what about the cost of storage? So here, this is they used to use level of cost of electricity, but we've changed that starting this year to use levelized cost of storage. But it shows that in this case, hydrogen is competitive with them. We still need some research to go on improving the round trip efficiency and lowering the cost. But even in the current and future and the 2030 projected cases, hydrogen over these periods can be cost competitive, particularly compared to batteries. Still with K's, compressed air and pumped storage hydro, it has a way to go. And this is for the 100 megawatts, and this is for the 1,000 megawatts. I'll need to make sure I add the nomenclature onto this slide. I apologize that I missed that. But of course, the other thing to remember is hydrogen can be used more than just for bidirectional energy storage. So we've been looking at, one of the things that Di Wu and his team has been looking at is energy storage evaluation tool. There's a whole set there, the batteries, microgrids, pumped storage hydro, virtual battery assessment tool, VBAT. I'm going to focus only in on the hydrogen energy storage evaluation tool, or HSET. And this is a tool that we use for modeling optimal dispatch and evaluation of hydrogen systems towards multiple delivery passageways in grid applications. It will project the costs, different areas. It uses compressors, and it has very, very flexible. You can enter all sorts of different information about it and change the configuration as you need. But it'll tell you, project those costs and the benefits and give you a return on investment. It looks at 3 different pathways, and the first pathway is we make the hydrogen, we make it at the electrolyzer, and it goes through, and then we can either we take it and we sell the hydrogen, we can put it back on the electric grid. All right. The second pathway is we can take that hydrogen, we can sell it, put it back on the grid, but we also can take it and methanate it, make it into methane, and put it into natural gas pipelines, which gives us a nice value. And we can sell that as a pathway. And the third one that we look at is, as we put it back on the grid, can we use, what types of grid services are we doing? So it's not just for the taking account for selling electricity back, but looking at ancillary services, capacity value, T&D deferral, demand charge reduction, demand response. We've identified about 11 different services here that they can be used. Now, of course, it depends on what you put into your system. Is it just going to be an electrolyzer? Or are you going to add storage or a fuel cell? So if it's just the electrolyzer, you can do some ancillary services, maybe a little demand response for the service that are available, but adding the storage and fuel cell gives you arbitrage, capacity, T&D deferral, and other abilities. And the more, obviously, the more services you add, it allows you to increases your return on investment. This is a web-based app that you can go in. This is a partial screenshot, but you get to fill out, you enter it has default settings, but you can enter your own for costs, enter your own for different financial evaluations, what your discount rate is, but also you can enter in the electricity costs and other things that have to deal specifically with the utility that you're dealing with and the part of the country you're dealing with. And then it will return out the present value benefits and costs and break it down to different components so you can see where they are. Sort of as a couple of quick examples here, try to make to show you some of the power of this, so that if we start off with just a 5 megawatt electrolyzer using one pathway that's just making it bidirectional, no grid services, these are the entry points. It gives us an ROI of about 0.41. If you see the benefits, the cost is, that's okay, not too exciting. Now, as we add in things, so we add in grid services here, you can see the ROI increases. We add in conversion of the extra hydrogen to methane. That is another pathway. Along with just those two grid services, the ROI becomes even higher, and the electrolyzer hours of operation also increases. And then as we add in storage and a fuel cell, and additional grid services, the ROI becomes very high. This was the best ROI in this particular scenario. But this shows you what the HSET tool is capable of doing and how it can be used. How it can be used for these type of services, for understanding and predicting what the benefits would be for using a hydrogen-based energy storage. This is pretty much my last slide here. So as I'd say, hydrogen grid scale energy storage has potential. It's the current technology is PEM technology based. You can either go with a PEM fuel cell and a PEM electrolyzer, or an alkaline electrolyzer coupled with a PEM fuel cell. Solid oxide is developing. I'm excited about that for various reasons. What excites the benefits for using hydrogen is that you're not just going from the power generation to storage to the grid. You have other areas and other places that you can sell the hydrogen over there to increase the number of benefits that you can do and increase the sales opportunities. DOE is funding R&D into key areas to lower the cost and make it more competitive. And the installed cost and level cost of storage is competitive, and we hope that it can get, as some of the additional newer technologies mature, that those costs will continue to be more competitive. With that, I'll end here. This little slide just has a very brief overview of some of the areas that PNNL works in, but I'd like to thank you, and I'd be happy to spend a few minutes taking questions.
Thank you, Jamie, for the comprehensive overview of hydrogen as a long duration energy storage asset and the opportunities in this area. There are quite a few audience questions, and it's a very engaged audience. They have a lot of questions about efficiency and cost. I'll go through as many of them as possible as time permits. So to begin with, for hydrogen produced by steam reforming, what is the efficiency for electricity generation using fuel cells compared to a natural gas power plant?
So, so you're looking at the starting with natural gas, making it into hydrogen, and then converting it back to electricity through some genset. Obviously, since you're making the hydrogen from natural gas, the round trip efficiency, or the efficiency of that scenario, will be lower than that of the just converting natural gas directly to electricity in a turbine. So typically a natural gas, if you're not doing carbon capture, is about 75% efficient to making hydrogen. And then you're going to have say you have a gas turbine, a 250 kilowatt hydrogen turbine runs about 65% efficiency plus or minus 5%. A PEM fuel cell will operate 65% efficiency plus or minus 10%. The difference being on the emissions coming from the natural from a hydrogen turbine versus a hydrogen fuel cell. And if you want to know about that, just in brief, hydrogen turbines tend to make NOx, and so you're going to have to include a NOx cleanup system on there, whereas a fuel cell will not make the NOx. Anyway, you can say 75% efficient times 65% efficient. So you're looking at that efficiency in about the 40s, in the mid 40s range. So if you're going to be doing that, the question there becomes, because natural gas to power plus CC carbon capture, and that I'm not sure what those efficiencies would be. I defer to some of my co-workers who work in that area. So that will cost you some efficiency. I'm not sure about that. It has to deal with what the carbon is. The natural hydrogen, I wouldn't be, well, that's the answer to that question.
Okay, there are a couple of questions about electrolyzers. For the solid oxide system, won't you have even higher efficiency once you use the high value heat?
Yes. So that's the exciting thing for me. There's a lot of things that I like solid oxide. That's what we do research on here at PNNL. I get very excited about it. So the electrical efficiency of a solid oxide electrolyzer is 98%. 98% electrical efficiency. It's amazingly high. So that is super exciting. The challenge is we have to provide high temperature steam. And so if I electrically heat that high temperature steam, I take water, I have to vaporize it, get it up to the temperature, that lowers your system efficiency down to in the 75% range. So if I have waste steam from a plant, say I work with an ammonia plant and it's exothermic, and we have some ammonia processes. Exothermic actually is a really nice coupling with this, or you can do various different things, different chemical plants. But if I have some waste heat there, so if I have steam, low quality steam, doesn't need to be high pressure. In fact, I don't want it to be high pressure. My efficiencies go from 75% to 85%. The higher the temperature of that steam, the higher the efficiency will go. If I have steam up to 600 degrees, that efficiency would be, you're now pushing 90+%. So you're correct. As you go up in temperature of that waste steam, and that waste, at that point, anything over 100 degrees, I don't consider a waste heat stream. But if I have a heat stream that's available at temperatures, then yes, I can get very high efficiencies. And then we can use, of course, we use various heat exchangers and whatnot to capture and reuse those efficiencies to make them reuse the heat as much as we can to take advantage of that. But yes, you're absolutely correct. It's a very exciting thing. And I love the idea of coupling it with whether it be a chemical plant, whether it be a nuclear plant, someplace that has heat. And then they work very well.
Okay, and Jamie, we have quite a few questions to go through. So if you can hit these briefly, could you please explain why, on the subject of solid oxide electrolyzers, why they would be low cost, considering the challenges of operating at high temperatures and the requirement for fancy ceramic materials?
So the reason why it's a lower cost than a PEM electrolyzer has to deal with the raw materials. The solid oxide electrolyzer does not require any precious metals. And so, yes, it is ceramics, but the ceramics are lower cost. Dealing with high temperatures, we know how to do that. And once you, by making sure that we're operating 750 degrees or less, we can stay away from exotic materials in the heat exchangers and what have you. Our cost comparison shows that we're very cost competitive with the PEM, that we can probably get down to $200 or so per kilowatt for the system there, as opposed to a PEM, which requires, a PEM electrolyzer will require platinum, titanium, iridium, gold, and naphion, all of which are very expensive. So it comes down to the cost. You are correct. The higher temperature does increase our cost, but we think that's offset by the use of lower cost materials.
So do the estimate of the cost of electrolyzers factor into the projections from major manufacturers that predict the price reduction of 70 to 80% will be achieved over the next 1 to 2 years?
Yes.
Okay, that's fantastic. Moving on to the alkaline electrolyzers, you provided only one number, 50% for the efficiency. Is that round trip efficiency? For example, is it 50% times 50% equals 25% round trip?
So that's a great question. Most likely, the alkaline systems that is just the electrolyzer. I didn't include the others because it depends. If you're going to use a PEM fuel cell, then that's going to operate at 65%. So 50 times 65, you're at 30%. Of course, you can. There has been some interesting research coming out of Europe at operating these alkaline electrolyzers at higher efficiencies. I'd like to see how that develops over the next few years, because they could get up to 60 and start rivaling the PEM electrolyzers in efficiency. And then that round trip efficiency will be upwards of 30, similar to PEMs. But that's the reason why I just included it there, just because I didn't want to mix the different types of technologies.
Okay. Next question. Instead of transporting hydrogen over long distances, isn't it better to put electrolyzers near the point of use and use the grid to bring in renewable energy?
Yes. That is when people ask me, that's what I tell them.
Okay.
Pipelines are available, but if you have to have a lot of need for pipelines before you do it. But there are reasons why people will want to transport the hydrogen as opposed to bring in the electric grid, having to deal with congestion, what have you, of the grid. But yes, that's what I advocate and I tell people to do. If they ask me, that's what I tell them.
There are a couple of questions on compressed hydrogen storage, and what is the percent of energy to compress hydrogen relative to the total energy stored? That is one question. And the second question is, if the parasitic energy is 35% of the chemical energy stored, is it worthwhile?
Okay, so that's a couple of questions there. So on the first one, how much the energy it compresses is needed for the compressor depends on how much you're going to compress it, or if you're going to liquefy it. So we'll start with liquefaction. Liquefaction actually is really energy intensive. That's how come they don't do it very much. It takes about 12 to 15 kilowatt hours per kilogram of energy to liquefy hydrogen using today's technologies. PNNL is working on a new way of doing that cuts that in half, down to about 5 to 6 kilowatt hours per kilogram. That's still high. A compressor, if you take it up to 10,000 PSI, that's pretty intense. You're talking about 3 to 4 kilowatt hours per kilogram. If you're at the lower ones, it's not, you cut that in half. So you're talking about around 2 kilowatt hours per kilogram. So how does that compare to the energy density of hydrogen? The lower heating value of hydrogen is 33.3 kilowatt hours per kilogram. So just the easy math, if you're using 3 kilowatt hours per kilogram, so you're less than 10, around 10% of the energy of the efficiency of the gas to get it there. There are research being done at using PEM and alkaline even systems to generate hydrogen at pressure, which would lower that costs. But there's challenges with that too. So I hope that answers the question. I can't remember. That was the first question. I don't remember the second question.
The second question talked about the 35% parasitic energy relative to the chemical energy stored when you compress hydrogen.
So 35% is pretty high. That is taken into consideration in the levelized cost of storage. That's how come I presented those numbers in there, and that is a challenge about it. It's just no way around it, and so we're looking at ways of lowering that. But so those numbers I provided in the lower LCOS do address that issue. It is included there.
Yeah, one of our panelists remarked that the panelists came here, not the panelists, the attendees remarked that they came here mainly to hear about hydrogen storage. So I hope this satisfies that attendee. There's a question about, can you touch upon different solid state hydrogen storage technologies?
Solid state ones. Yeah, there's different ways we can store the hydrogen in the solid state. You can use what's called a metal hydride. We can also do it through chemical. We can do it through different carbon foams, carbon nanotubes, MOFs, metal organic frameworks. That's a MOF, and there's ways to do it. So let's break this down. That's a really complex question. I could spend an hour on it, and Ram knows me, and it's really hard for me to give a brief answer, but I will endeavor to do so. The metal hydrides, they typically store 1 to 3% of the weights of the metal. Is stored. Hydrogen can be contained in there. The challenge you have with the metal hydrides is cycling them and getting to high capacities, and they typically have exotherms, and so it's designing those tanks to handle the heat that is generated as it absorbs the hydrogen. You have to dissipate that. Then you have the heat that is needed to get it to release hydrogen, so you have to bring it in. So that you have to have this heat exchangers going on in there. But there is a lot of talk in doing that. There's advantage volumetrically. There's some advantages to doing that. There's some interesting work going on in Japan. There's some interesting work here in the States, also engaged in those different areas. Moving on to the MOFs, the carbon nanotubes, those type of things, those are all typically done at what we call cryogenic temperature. So you're talking about 80 degrees, about the temperature of liquid nitrogen. So you're going down in temperature, and then they can absorb a lot of hydrogen, and they work pretty well. And going at those temperatures, it gets exciting there. The gravimetric looks really good. The volumetric is a challenge. And then you also have to go to higher compression. So you typically can't do it at room temperature. It does need to go to higher pressures. 200 bar is some of the numbers that I keep hearing tossed around. So there is interest there. The questions become is, how much. And then you're going to have the heat issue also. Then the other challenge you're going to have, and I forgot to mention this for the metal hydrides, is speed. How fast can you get the hydrogen out? And so there is work being done in these areas for all this, and how to do that, and that the kinetics go involved, and how to do the heat mass transfer is a big issue. There's a lot of R&D going on there. I didn't touch on it that much, because for the larger scales, well, the metal hydrides may work. There's just a lot of challenges. Really in a nascent phase.
So Jamie, your talk has attracted tremendous engagement from the audience. There are at least 6 or 7 questions we are going to leave on the table because we are running out of time. I want to thank you and the audience members for a great webinar. And I want to remind you that there are several interesting webinars coming up in this series over the next 3 iterations. We have Dhruv Bhatnagar talking about capacity expansion planning, the role of long duration energy storage on August 11th. On August 25th, Christine Holland will talk about machine learning for energy storage. And then on September 8th, Mark Willey, our supply chain expert, will talk about challenges of supporting the US energy storage industry with lithium-ion batteries. He'll talk about supply chain issues, all very interesting topics. I hope you all will tune in and continue to engage with us in this energy storage webinar series. So thank you very much for attending, and special thanks to Dr. Holladay for a fantastic talk today. Thank you.